So to figure out what you're going to do, just kind of, some of you who were in my 401 class, I said, hey, you guys, you've done, go ahead and try this course out. And so you may not have thought as much about what you're going to get from this course, but it is about distributed systems, okay? So let's start to define what a distributed program is. You guys have done, a lot. You've done 401, you've done 110, you've done 410. So you know how to program. So somehow this is about programming in a distributed context. We should know what a distributed program is. And so what's different? The difference between a distributed program and a non-distributed program. Let me ask you. Yeah.
The resources are distributed out across multiple systems.
So we use the word resource. Okay. We can define a resource, or we can give example. And so the resource examples are
Processor.
okay. So use the word resource, we use the word process, we've used memory. Okay. So the processes and so process versus memory, somebody want to expand on that?
Sorry,
Process versus memory. So process is a resource, so is memory. Mm-hmm. How are they linked?
Processes work on virtual memory, and virtual memory is not actual physical memory.
So okay, good. So resources. So memory is an example of resource, and processes, you said, work with virtual memory. So who accesses resources? Yeah.
Well, the processor, because it interprets the instructions in memory.
So processor, you said?
Yes.
Okay. So at the hardware level, so there are hardware resources and there are maybe non-hardware resources. Okay. Memory is a hardware resource. So a processor is a hardware resource, is a hardware entity, and it accesses memory. Okay, so that's good. You can think of that itself as a resource. Okay. Can you think of software resources also? Things that are defined purely by software. Some few people have answered. Somebody else? Yeah.
I would think that there are trade-offs between complexities of code, and there's also trade-offs between complexities like event notations, things that take longer, things that don't take longer.
So I just want, I understand there's lots of trade-offs, and those trade-offs may influence what resources we define, right? So what's an example of a resource that is defined purely by software?
What language do you use? What ISA you're using?
So that's I dropped what?
Instruction set architecture.
Okay, so that architecture is part of the hardware, you would say. Okay, yeah.
Threads.
Threads. Okay, so threads are entities, at least in conventional CPUs, are defined at the software level. GPUs tend to have them built into them. Other resources, something that's even more passive, yeah.
Device drivers.
Sorry.
Device drivers.
Device drivers, that's a piece of code, and that's something we write, yeah.
Going along the distributed notion, the fact that certain computers might have a certain program that others do not.
Okay, so that's to justify why we need distributed things, and so then we talk of programs.
So certain computers will have that resource that is software that others don't.
Okay, so software itself you think of as a resource. For you OS guys, I want to sort of put on your OS hat. When you think of OS, what are examples of resources? Nishir?
Probably something like either, let's say, a kernel or maybe a scheduler is working. So do you have this time slice? Do you not have this time slice?
So time is a resource.
Yeah.
Okay. So
Virtual memory.
Virtual memory. Okay, that is actually also defined by hardware. Software does the mapping, but hardware defines it. But so memory is a resource. Okay, and we think of resource typically as being passive. You can think of processes also being resources, but typically the resources are some things that somebody needs, and that might be the processor, or that might be the what's an abstraction about user or you guys have used this term already, something active that is defined by the software. Yeah, kernels, sorry, threads, and something, not every program has threads, so process. Okay, so ultimately resource is something that a process uses. Now process itself can be considered as a resource by another process, and that's excellent when you're talking distributed computing. That's exactly what you want to do. So ultimately, whether there are threads or not, that's moot. Okay, but what's important is there are processes and there are resources. Okay, and now we are talking about, okay, so now that we kind of know, and process can be a resource too, but typically processes use resources. Okay, and process, what's the difference between process and a program?
Process is a running instance of a program.
It's an execution instance. So the library code, the program, the kernel, that's passive pieces of code. The language, that's a resource in a very abstract way. But we are really talking of what processes need to do their work. Okay, and that might be other processes, but in a non-distributed system, that's typically disks, time on the CPU, and what's an abstraction above a disk that's defined by the software? File. Okay, typically file is the first thing that comes to mind when you talk of resource, and memory, of course. Okay, but memory is defined by the hardware, even though the mapping between virtual and physical memory is done by software, whereas a file is basically an abstraction. And typically the a resource is something that multiple processes can share. Okay, that's when you talk of OS, it's always some shareable entity. Okay, so again, another process might be something that's shared among multiple processes. So now let's go back. Now that we kind of know some of these terms, what's a distributed program? The one thing is, why do we need distributed program? Okay, but what's a distributed program now?
Where the resources are spread across multiple systems.
So that's what he said, right? Where the resources are spread over multiple computers. So the files may be resources, but resources are spread over multiple computers, right? Each computer has a resource. Your computer has a resource. So what's a distributed program? How do we define it more precisely? It's a program that
Can use the multiple resources from multiple.
it can use resources from multiple sources. Okay. And what if? Okay. So that sounds good. What if the program just creates a bunch of processes that run on multiple computers? Okay. But they don't talk to each other. They just go about, do their work like a shell. Would you consider that to be a distributed program? A shell is a distributed program? You can have the shell, yeah.
Wouldn't it depend if it runs on multiple processors?
Sorry?
Wouldn't it depend if it runs on multiple processors?
So would it depend if it runs on multiple processors? And yes and no, because the processors on which a distributed program runs is decided at execution time. So the program might be distributed, written distributedly, but it may all run on one computer. In fact, all the demos we'll create, most of them, will run on one computer, even though you'll be running distributed programs. So, but that's all right. If it's not going to run on multiple computers, then it seems strange to call it. If it doesn't have the ability to run on multiple computers, then it's certainly not a distributed program. Okay? But it might have the ability and not use it. Okay? But something else. So a shell could also fork processes on different computers. You can have such a shell. Right? So supposing we have such a shell that forks multiple processes and they can run on different computers, would you call such a shell a distributed program?
It depends if the process is running exclusively on a single computer once it has forked them. Like if a program from computer A forks a process from computer B, and it works on all the local hardware of computer B, then I would say it's not a distributed system program. But if that process has the ability to utilize even further more computers to do its bidding, I would say it is a distributed program.
So, okay.
Does it have to use messaging capability? So if the program has the ability to fork to multiple computers, it could be a distributed program. I think what NJ is saying is it may not run in using multiple resource pools, but it could be by access of, or by virtue of the messaging network between each of the computers it's forking to it is a distributed program.
Because without IPC, does it even make sense to fork to different programs?
So IPC, what does IPC stand for?
Inter-process communication.
Okay. So you guys are getting into the thing that somehow the program should use resources on multiple computers, right? The program meaning all these processes together. Okay. So each of them runs on one computer and never talks to any other process, which is what you're getting in IPC, which is what the shell does. Shell doesn't know what it's forking, it just says, go ahead, go ahead, go ahead. So if they don't talk to each other, then it's just a time-sharing system. It's not a distributed system. So there has to be some coupling. Okay? And that coupling can be in many ways, okay? But typically the coupling is called inter-process communication, where the processes do talk to each other. Okay? And so I think we've got it. It's a program involving multiple computers, okay, or at least the ability to involve. But the specific computers are bound at runtime, okay? And you might just go and have it run all in one computer, which means the program can run on a single computer. And the definition involves processes. So without the definition of notion of a process, we can't define what a distributed program is. And so we defined a process as an execution instance of a program. And the word thread has been used also. So what's the difference between a thread and a process? Yeah. A process can have multiple threads. Okay. Yeah.
A thread only has its own stack, a process has its own heap, code, etc.
Okay, so both the process and the thread, they are similar in that they have stacks associated with them. Okay. But a thread only has a stack. And where does the heap come from?
The heap comes from the parent process.
So a thread is contained in a process, as we just saw, and there is a parent process which defines a heap, a memory address space. Okay? So the threads in a process execute on the computer on which the process is executing. Okay? Whereas the processes can go and execute on any computer. So that is why we are not talking of this fine-grained concurrency interleaving, which happens with threads, but we're working more with the coarse-grained concurrency, which happens, when these address spaces are disjoint. And when they're disjoint, they can be on different computers. Okay, so the same program can result in multiple processes. And when you do a Control-Alt-Delete on Windows or do a PS on Unix, you see the processes. So they can interleave or execute concurrently. Okay, and so is a thread, but associated with the process. It's always associated with the process, and it's got its own stack. Okay? So yeah.
I have a quick question. What's the difference between a distributed program and a distributed system?
It's the same thing as far as we are concerned. Okay, so distributed program is something that can create multiple processes, and you may system is a very general term. Yeah, so we're not making a difference between that. Okay, so this is the pictorial description here. We have processes with threads, and different processes can execute on different distributed computers, whereas different threads execute only on one machine. So, is the shell a distributed program? We answered that. So there has to be some connection, some coupling between the processes that we're talking about. Okay? So if there are n processes, if there are two processes, there should be connection between them, right? If there are n processes, how would we define this connection?
Pipe.
Sorry? Pipe. Whether it's a pipe or, pipe. So pipe is a very general term. But the Unix pipe is a specific form of IPC. So yes, sure, you can have A send its output to B, send its output to C, and have them chain together. That's one form. Okay. So that should be an example of a distributed program in our definition of distributed program. And what we have is B depends on A, C depends on B, D depends on C, right? So in general, when we have n processes, we should have some kind of a fully connected graph. Each process depends on every other process.
Should be acyclic.
It should be acyclic, or it could be cyclic too, right? There could be symbiotic relationships. In pipes, it's acyclic. But you can imagine that we have two processes doing some data mining, and one process computes something and tells the other process, hey, don't go and do this part of, don't search this space, and then it finds something and says, hey, you don't search this part of the space. Okay? So
Maybe the processes could be cyclic but symbiotic, but perhaps the resource allocation graph cannot be cyclic. Maybe the resource allocation has to be not a DAG.
So resource allocation, not a DAG. What does that really mean? But have you looked at deadlocks ever? Have you studied deadlocks? So there is what resource can be held while another resource is being requested. Okay, that forms a graph. That forms an edge. And sometimes to avoid deadlocks, you try to avoid having cyclic structures there. Okay. So if you guys did operating systems, and if you have a monitor that makes a method call another monitor, that should not make a method call back in the previous monitor, because you'll get into a deadlock. Okay. So indeed, in that sense, yes. Okay. But in general, when there are n processes, what if, this is what I want to make sure. I want to make sure that's not the case that, so what does dependence mean? We can talk of direct dependence or indirect dependence. Okay? Let's talk of transitive relationship. So A depends on B and B depends on C, then A depends on C. So if we talk of this kind of dependency relationship, should every process be dependent on every other process? No? Or have a connect, or be dependent on. Sorry.
Or are we getting into like failure tolerance yet?
I'm just trying to get into distributed program. Okay.
Well, I would say failure tolerance is an aspect of distributed program.
It is. But it's, people.
Well, I would say that you should pair A and B and C, and then A has an indirect pairing with C.
Right.
Like a weakly connected graph.
Right. So if we there should be, between any two processes, there should be some coupling, direct or indirect. It should be not the case that we can partition the process into two sets, where one set works independently, another set works independently, and there's just no linkage between them. Okay? So every process should either depend on or be dependent upon by every other process. Okay? So that's sort of just distributed program. Now failure tolerance goes to multiple levels, and it can be zero failure tolerance or more. Okay? So some computation of a process can be influenced by or influence computation of the other process. So each process is coupled to at least one other process in the group. Okay, and basically have a what I said earlier, that every process should depend on every other process or be dependent on, okay, directly or indirectly. So basically, this is the definition. Graph trade, we're creating pairwise dependency links, is not partition every node reachable from every other node. That's kind of the definition we'll go by. Yeah.
So would that allow two leaf nodes to be indirectly dependent on each other?
Sorry?
If we have like two leaf nodes on opposite sides of the tree, are they indirectly dependent on each other because of their shared ancestry?
Yeah, exactly. So basically, the connection graph is not partitioned. Maybe they're not dependent on each other, but basically the graph is not partitioned. That's the key. The dependent, independent is not as important as this. Okay. So, distribution versus concurrency. So, is every distributed program a concurrent program? A concurrent program is a program where parts of it can execute concurrently or interleave. So is every distributed program a concurrent program? No? Why not?
Because you could run programs sequentially on like a blocking, like one by one instead of run.
So what's a concurrent program? Concurrent program is a program that has multiple stacks. Okay, that is it. Now, whether they synchronize with each other and one goes at one time, the other goes the other time, we'll still call it concurrent. Okay, the very fact that you made multiple processes or multiple threads means that you think there are some activities that can go at the same time. Okay, so yeah, theoretically they could all go in lockstep, and we would still call it a concurrent program because there are multiple threads. Okay, so we're going to be a little loose there. But you're right. Technically speaking, it shouldn't be the case that only one instruction can be executed at any one time, okay, which is almost never the case. So every distributed program is a concurrent program, but every concurrent program, you can have is not a distributed program, right? So we have distribution, but no fine-grained concurrency. We have concurrency, but not distribution. And I'm saying that typically we have distribution and fine-grained concurrency. It's almost, in any practical program, when a program is communicating with other programs, there are greater reasons to have threads within it. Can you guys see why?
Because if one thread just blocks on communication, it's just a waste of a resource.
So we might have a thread that is communicating with another process and blocked. And when that's blocked, we would like something else to execute in that program. And we might, so threading, if those of you who guys have who have done OS or have just used threads, why do we create threads?
To optimize tasks that do not depend on each other's computers.
So to do exactly what he was talking about, to make sure we don't stall and we don't have to stall. If we break up our task into multiple activities, then some activities can go concurrent, go execute, but other ones are not. And there's also software engineering. So those of you who did 401 with me, do you guys remember why you created threads there?
We created threads to animate concurrent action.
So there were 2 or 3 animations that could go at the same time. Okay? You could have written it all in one thread. You could have had one thread that does part of the animation, one animation, then goes in does part of another animation, then goes back and does another part of the first animation, and it would be doing what an OS does. It will have basically a context block for each animation. It will load that, do the next step, then say, okay, I've done enough of this, let me go and do the other one, and so forth. So threads are also used for software engineering. They just make your code less ugly, but doing what the OS would do. So when you have a process talking to multiple processes, maybe each communication is kind of an independent activity, it's like an animation. And you might just want to have multiple threads, even if they're not blocking. Even if they're non-blocking, just break your program into multiple threads because it's cleaner. Okay? So these are both reasons why you would have typically distribution and concurrency together. Okay, so threads is going to be extremely important, okay, for this class. Okay. Questions?
So when you have like multiple threads and you're splitting those threads across multiple systems, won't the risks of threading also increase?
Risk?
Yeah.
You mean all the problems that go with threads?
Yeah.
Like what kind of problems?
I'm talking about anything from like, let's just say something like I have a critical section. Navigating the critical section would become exponentially harder now because it's not just creating a global lock or doing something like that. You have to communicate that lock across systems.
And what happens when you don't have these things? You have what is called race conditions. So, the joy of programming in this course is going to be dealing with all these uncertainties. Okay? Which thread is executing at any one time? How much time did the message take to pass by? So we are going to, in fact, when we talk about, now the word exponentially, you're saying every combination creates a problem. So hopefully your program is written in a somewhat systematic way, okay, where things are partitioned to some degree, okay, but the risks are certainly higher. You know, whenever you have power tools, they can hurt. So we are going to, this program is, this course is going to be difficult, not because of the amount of code you write. Those of you who've done 401 with me, the code you write here is a very small fraction of the code you wrote in 401. But, you know, what did you learn in 401? Debugging sequential programs. What you learn in this class? Debugging distributed programs, okay, which are also concurrent programs. So in OS, you guys, you know, learned how to implement concurrency, and you took some classic problems and, you know, read Dunning philosophers and other problems and learned how to code them up. And now you're going to be dealing with all kinds of new problems that you haven't seen before, and you'll have to sort of figure out, and I'll be providing you with help on how the synchronization goes among them, and so that's going to be it. So you're going to really learn threads and see why all these concepts you learn in operating systems, apply them to real tasks. Okay. So non-distributed creates a single process, unconnected to another process. Must deal with sequential and possibly concurrent issues, creates a pair or larger group of connected processes, and must deal with distribution and usually concurrency issues. Okay, so this is why this is. So those of you who said I'm interested in systems, this will all get put together. Okay, it'll put programming, it'll put networking, and it'll put operating system stuff all together. So this is this is an integrative course in that way. Okay, so let's talk of some examples of distributed programs. And we sort of I saw from you some examples, and we saw some conditions of why we might want distributed programs. But just tell me, what are some driving applications for distributed programs? Sorry? Blockchain. So that's a distributed, yeah. Military, so what kind of application are you thinking? So some kind of distributed program that is fault tolerant?
Yes.
Yeah, absolutely. Give me some little bit more concrete application. Yeah.
Like something like a Google or an Amazon data center.
A data center, okay, where you are. So what's a data center? You want to define what a data center is?
A data center is where a request is broken down into multiple smaller requests and is fed across multiple systems, and the answer is constructed back together piece by piece.
Okay, so that's one part, that the task is broken into subtasks, that's 10. And each subtask is done by only one computer?
No, there's like levels, and each level down, it's like a tree which is expanding.
Okay, that's fine, I understand that you break it into subtasks and subtasks. But would any two processes be coupled, you know, at the same level also? Will there be some kind of...
It can be, it cannot be.
So when he talks of fault tolerance, what comes to mind when you think of fault tolerance?
I mean, I can say.
Yeah.
Byzantine general's problem, how many pieces of misinformation can you receive back and still be accurate piece of information?
Okay, so one part here is fault tolerance is that I give the task to you and you say, here's the answer, but you give me the wrong answer. You give me the wrong answer for various reasons. One could be that the program was wrong.
Let's use like blockchain validation for that. So like one computer says they solved a portion of the blockchain, they solve the next step.
Okay, so you're going a little too fast. So let's go and talk of first what, you know, that I give the problem to somebody else and they give me the wrong answer. Okay, now why did they give me the wrong answer? One could be that they computed the wrong answer. So let's go, you know, let's try to define what Byzantine means. And what other reason might there be?
Something went wrong in the hardware or the network.
Something could have gone wrong, yeah. Data got corrupted, so it's, okay, yeah.
That's just a communication error.
Yeah. So are these examples of Byzantine failures?
Yeah. And like
anybody else?
Processing, that'd be an example.
Anybody else?
I mean, a different kind of fault tolerance comes into mind where you could be using something like at the disk level, let's say you could be using RAID, or at like a network level. You could be
So
using
what is the concept that's going on in RAID? What is the basic concept for fault tolerance?
data replication.
Replication. Okay. Byzantine is So where's the word Byzantine come from?
The Byzantine Empire was city to city, and they had 9 generals surrounding the city, and they had to send messengers to each of the generals to coordinate whether to attack or retreat different times, and several of the generals wanted them to lose. So they had to be able to communicate between the
So
generals.
that's not to do with errors. That's not with code functions. That's to do with not trusting. Okay? So that is the Byzantine problem, where we don't even trust some agents. And we have to make sure in solutions here that there's only so many traitor generals. Okay? So Byzantine is something we will not look into in this class. Okay, that gets into a whole, and in data centers, when you're talking of an Amazon data center, I think you can be pretty sure that that's all localized and we don't have to deal with Byzantine failures here. But yeah, if you're trying to find the meaning of life and have given the problem away to the whole world, then there will be some people who want you not to find the meaning of life. So then at that point, we'll worry about Byzantine. Okay, so Byzantine is just this whole hairy thing subject, and that's something that's best done at a grad level with theorems. Okay, so my first distributed class was all about Byzantine failures. Okay, and that was as a grad class student. But we're going to talk a little bit more mundane, if you will, where we're going to constrain the world, and that's why we're going to worry less about blockchain and Byzantine, because we're not going to. It's not a question of trust. Okay, it's a question of corruption. It's a question of some failures, and we're going to assume that failures are rare, and so deal with algorithms, come up with algorithms that involve that. Okay. So examples now again are,
Possibly a national sort of distributed file system for health records and moving test results from like across the country instead of transporting a patient to get sort of tested or something. You could send all your data there, have the computations done there, and the results come back.
So having a global file system. Okay. In fact, distributed file systems have been the driving problem for distributed computing. Okay. So and even if it was first a local area file system, then and we know that. I mean, is there a national file system today? Does AFS is kind of supposed to be in that direction, but for various reasons, because you need identity, you need notion of a user, it gets to be tricky. But there are, and you'll use one of these systems, in fact, in your programs. But there are systems that are sort of like file systems, like operating systems, with a distributed data store. Okay, where you can do all this computation, you can have sharing of data, and you can then fork off. So that's cyber infrastructure. AWS is an example of something like that. Okay. Other examples? Yeah. Sorry. The internet is something how to make the internet itself. It's a distributed system. How do the domain servers talk to each other? That's a distributed system. That's good. Yeah.
Like just any web application.
Any web application, any client, anytime you interact with use a browser, that's a distributed application. Okay. Okay. Any other buzzword?
Content delivery network.
Sorry.
Content delivery network.
So some kind of streaming thing services. Sure, absolutely. Okay. Yeah. Others? Internet of Things. Right? So, the right question is not what is distributed. The right question is what is not distributed today. Anything is potentially distributed. Okay? If you've got an application, you probably want it accessed from the whole world. Okay? And so we can have distributed repositories, which is sort of what you're talking about. You guys talked about resources being shared, so having the ability to go and print at some other remote location, that's a distributed system. Okay, using some of the file, disaster prediction, some military and government agencies, that's a big area. Computation distribution, so big data, you can do it locally. You can do sorting on your own computer. You don't need multiple computers, but maybe it's faster. Maybe, okay, it's typically not faster by going distributed, but it may be certain computations, finding the meaning of life. That might be, or finding whether there's remote life somewhere else. That could be something that we might have the whole world be interacting on. Okay, and my own research area is in collaborative applications, which means there are multiple people from different computers, and that means you have to have a distributed program. Okay, so there's all these examples, and now the question is, okay. So there are many questions. So as you guys know, we made OS or networking to be a prerequisite. I didn't do this myself. This course was taught by Mike Reiter once. He didn't teach it again after that, but he's the one who made these prerequisites. And they made sense to me. So ideally should be OS and networking, but then we'd have even half the size of this class. Already we've got a pretty big bar. So what's the relationship between OS and networking in a distributed course in distributed systems? Like I said, ideally there should be both. Yeah.
Networking is about how it communicates with each other, how it validates the information that's being sent and received.
So networking is about communication of information. And what are the endpoints of the information? What is the source and what are the entities that is the source and the destination of information? Sorry?
The resources on the OS.
So information is being communicated. Some actor has to be involved, right? That sends information, and that some actors to be involved that receives information. So what are those actors? Yeah.
Hosts and systems.
Hosts. Okay. And what are we talking about in our world? What are the actors?
The processes running on those.
Processes. That's a big difference. But information has to go through a host before it gets to a process, right? So they're related, right? So that's the thing that we're going to take. We're going to essentially build an abstraction above networking. Okay, and if you use sockets in your networking course, that is an OS abstraction. That is not an networking abstraction. Okay. What about OS? How is the OS involved? Yeah.
Well, you used a lot of, when you were trying to describe what a distributed system is, you compared it to a lot of things in the OS, so that can be used as a stepping stone to understand.
It could be used as a stepping stone to understand. Right? We are talking of basically information leaving a process and coming to a process. Now, information could leave a process and come to a process from another process. It could also be it could be just a regular old hello world program. The information is going from a process or from a CPU to the monitor. It's going from one device to another device. It is a form of what is called I/O. Right? So there's input and output, and there's a notion of blocking. Okay, when I do a read or a scan, I block. When I do a write, do I block? When I do just a hello world, is there any blocking involved there, all you OS people? And do you guys know what exactly happens when you go and say print line hello world?
If I'm not wrong, there's like a monitor hole in the memory, and that hole has the VGA buffer which gets flushed and reset. And I don't know exactly how that is being done, but depending on the implementation, there might be blocking, if I'm not wrong.
Or just a regular old, so that's, so you guys are on 411 also, right? You know what interrupts are? So there is, in fact, when we talk of concurrency, even if you've never done threads, you have dealt with concurrency because underneath the devices act concurrently. Okay, and that's where I/O is involved. So whenever information leaves, whether it's a particular form of device that you're talking about, another or a dumb device, there is a notion of I/O. So pipes that we just saw, you can either receive information from a user or from another process. So they're related. So OS is very good about I/O management. OS is the one that defines what I/O really means. And we're really talking of remote I/O. Okay, I/O that is inter-process I/O. That is what IPC is essentially. So understanding OS, I would say that OS seems less related to distributed systems and networking, but the concepts that are fundamental in OS are far more relevant to distributed systems than actually, I would say, networking. Okay, that we can just hide away. So, but they're both important. So, interrupt management, thread communication, thread synchronization, thread management, all this stuff is stuff that you learn in OS, and that's going to be relevant in our, we need to know threads. Like I said, our programs will have multiple threads. So if we don't know what threads are, we're in trouble. Okay? And the abstractions we will use are very much high-level interrupt routines, if you will. They're just abstracting over interrupt routines. And in networking, you have you have all these layers, and we're just going to build another layer on top of it. Okay. So we're going to have distributed systems. Can you think of distributed systems themselves being layered? So I think I've convinced you that the concepts of distributed systems are layered above both networking and OS. Okay. And can you think of the distributed system itself being layered?
You have layers of sort of authority that manages, like, I'm just going to use an abstraction of, like, for countries, how a country will have, like, its capital, and then its provinces will have their capitals, which administer their regions, have smaller counties, which administer their areas. So, in a similar way, you could stack it up like a pyramid.
But, so that's good. That's a good way of breaking up things. And you're saying that there are regions of control.
So basically, the smallest leaf could not contact the top leaf. It would have to go through the whole chain.
Okay. So you're talking of some kind of modularization in the program. And, Nisha asked me, what's the difference between distributed systems and a distributed program? And I said, none really. But I do want to say that we're going to look at distributed computing from a systems perspective versus what is the opposite of systems? Or what, if when you guys do when we divide areas, subject areas into multiple categories, there's systems and there's what else? Networks are considered part of systems. When I talk of, breaking computer science into multiple areas, so we say these are the systems courses, right? And what other kind of courses do people offer? I mean, this is very vague, so I understand if you guys are a little confused. But what's sort of the opposite or opposites of systems? Theory. Sorry? Languages I would consider part of systems. That's abstractions. Applications. Okay. So when you're talking of this breaking up of this kind, that is very application specific. And we are not going to look too much at application specific things. We're going to look at things that are common to many applications. How do you divide the labor up? And indeed, you might have that, when he was talking about farming a task into subtasks and sub-subtasks, that's exactly what you're talking about too, that we just fork off and that computes maybe this part of the data, these two together compute something about a larger piece of data, which is like your regions. Okay? But I'm just talking of systems, which is basically application independent. The difference in theory and system, what is the difference so application is basically something that is not common. So any layer that is common to multiple applications, or arguably any application, which is systems. And theory, different in theory and systems. What you've done in theory courses that's different from in systems courses? Proofs. Okay? Which is basically you get into the details. And the equivalent of these details in systems courses is implementation. Okay? So I can take a program and I can go and formally describe that using logic, or I can just give you the code. They're both formal descriptions. One may be easier to deal with than the other, and I'll let you guys decide which is easier. Okay? But that's the thing, that we're not going to look at proofs, but we will look at enough details so that we understand the devil in them. And that'll be through implementation and debugging and seeing race conditions rather than through proofs. Okay, so it'll be more. So we're looking at abstract layers. So given that we're working at levels of abstraction or at the systems level, can you imagine? Why things might be layered in distributed computing?
It's like, why are things layered in hoops?
But what are the examples? What kind of things? Yeah, sure. Why is layering? Yeah.
Could it be like in networking where things are layered in protocols to make sure that everything can operate without knowledge of one line?
Right. Exactly. The same reason we want layers here too. That we want levels of abstraction. But can you think of what kind of levels that are application independent? Can you think of some examples? Messaging. So messaging is one layer. Okay. When you say messaging, what might be layered above it? So we saw that TCP, IP, and UDP, they involve communication of bytes between hosts. So one abstraction above that is communication of bytes between processes. Okay? Can you think of some abstraction above that?
Communication of bytes among different computers altogether, maybe?
That's exactly what networking gives you among different computers. Yeah.
Rendering the bytes?
Sorry?
Like rendering, bringing them to human form.
So why is a byte not a human form? But you're on the right. Exactly, you're saying exactly what I want you to say. But I want you to say a little bit more. How many of you have done How many of you have written a distributed program in Java or some non-C language? What did you use?
Java.
What did you use for communication exactly? Which part of Java?
Java.
No. What did you use?
Can you repeat the question?
I mean, what did you use for interprocess communication? How did you do messaging in Java? What part of Java?
We're using like a message broker, and then basically like it handles automatic messaging between like the different systems. Yeah.
So you had a message broker, which was part. Did you do it in an internship of some kind?
Yeah.
So you didn't quite know what was going on underneath.
No, I was doing the other parts, but
Yeah.
the messaging.
Yeah.
So I've used Python before, so something like RabbitMQ instead of
Sorry.
RabbitMQ, so I can distribute this.
So what did you? So when you send information, did you was the information human readable, or what was the exact block of data that you sent? Bytes? Did you send bytes, or did you something else? Send something else?
I'm not sure, but I think send some kind of task or data or any object.
Okay. So yeah. Go ahead.
So an SMTP server, we just sent bytes, but I never actually saw what it sent. We just encoded it.
Yeah, but you send bytes, right?
Yeah.
But the user wanted to send an email message.
Yes.
You converted that into bytes in an application specific way. Is there some application independent way to convert something more human?
JSON or XML.
Okay, so you're basically serializing the data into bytes. You're sending an object. Okay, and so that might be one layer of abstraction. Then we were talking about blocking, non-blocking. So non-blocking is sort of like interrupts. And then you can imagine abstractions that go in, block instead. That's another variation. So firstly, we are seeing there's variations in IPC. When there are variations, they may be layered, or they may not be layered. Okay, but the point is that there's no one best method to go and send messages, because at some point we might want non-blocking semantics with all its problems. Okay, because of flexibility. And sometimes we don't need the flexibility, so we'll take something more controlled. Sometimes we want to send bytes because of flexibility, and sometimes the JSON data that we're sending is just sufficient for our needs. Okay, so that is an IPC, and let's talk of failures. Can you think of failures introducing layers also?
Yeah, if you hit a failure at like a higher level, you might have to step back up a level to reprocess the level you were just at. Or if you hit a failure at a much lower level, you
So levels of failure you're talking about. So what might the levels of failure be?
It would matter more if you failed in the beginning of the program than if you failed at one of the smallest processes in the program, because you could just reiterate through that process of the program on a different node, and then you'd have the same answer back. But if you failed during what NJ they're called one of the critical phases of the program, you might have to start over.
So the recovery might be different. Yeah.
I'm thinking of a bit more hardware area. So let's say there's multiple sectors on the disk and one of the sector fails. So you know at the level of the disk that the sector has failed and you are remapping that sector to a spare sector on the disk, let's say. But at a higher level, you do not know that happened. You just think the disk is still working perfectly.
So again, what you guys are getting into is a little bit more application-specific stuff. But in general, you can imagine that there's multiple levels of failure, of tolerance. Some algorithms may be tolerant to more failures than others. Okay, you can imagine that. Some may allow Byzantine failures, some may not allow Byzantine failures. Any algorithm that allows Byzantine failures also allows other kinds of failures. Okay, but not vice versa. So there's going to be so you're going to have multiple layers because of the different degrees of different kinds of failures and different degrees of failures. Okay? And remember, even networking does go and address one kind of failure, right? What kind of guarantee does networking give you? Does it give you any guarantees? Or, yeah.
I mean, reliable data transfer.
Reliable data transfer.
Certain things.
You know, TCP/IP will give you reliable data transfer. So that's one form of failure tolerance already. Distributed systems are going to provide you with more failure tolerance, and you can imagine there being multiple levels there too.
Quick question: how do you define safe data transfer? Because there's always packet loss. There might be packet loss.
So how do I define what?
How do you define
Reliable data transfer?
Yeah.
So what do you think happens? Have you done networking course? So what do you think so we'll look into that, but what do you think intuitively happens when, to allow communication to be reliable?
So UDP doesn't have verification of something being sent, something being received, or the order for it, versus TCP has all of them. So you have what you just call logging. You have the access to be able to confirm that something was ordered, sent, and received, and then that it was data validated. So
There's validation, and there's also what else? Networking guys, what else that happens to make TCP/IP work? If a message gets lost, checksum, that's parities, and then retransmission. Okay, so you keep trying, and then you have timeouts. You really need timeouts, and at some point you say, "I give up," even though that might, even though there may be message in transit, you just say, "I give up." Okay, so we're going to have multiple levels of. So now that you understand this, let's try to figure out what we're going to do in this course. Okay, and so what I've got here is are the basic courses that you might have. You can break up your undergraduate course or any kind of curriculum into multiple circles with courses like compilers, operating systems, programming languages, data structures and algorithms, and then there's all kinds of applications courses and toolkits. Okay, so MapReduce might be a toolkit that somebody provides you, for instance. So all of these things are related to distributed computing. If I have a programming language, I can imagine a distributed programming language. If I have an operating system, I can imagine a distributed operating system. So I've taken the basic curriculum that we have and said that everything that you've learned has a distribution angle to it. Okay, if you're going to talk about collaboration and mobile computing are inherently distributed. Okay, IoT is inherently distributed, but some things are not inherently distributed but can be made distributed. Okay, so how do we teach? Given that an existing curriculum, how do we go and teach distributed computing? Given that traditional curriculums do not have distributed computing in them. And one method is that we take each of these areas and teach a distributed analog of it. Okay? And in fact, there are people talking about that. I just went to a workshop earlier this year, or late last year, where they were talking about, in data structures courses, talking about concurrency and distribution. in programming language courses doing that, but that's not how we do things right here. Okay, and it's got in pros and cons. So, if you're going to have one course, just as that's a constraint we have here, what do we pick from all of these? What should go into that course? That is a challenge that's faced by anybody trying to teach distributed computing. And arguably, you would like to say that we'd like to do the most fundamental parts, right? If you're going to do the most fundamental, among these particular courses, I've got, which do you think are the more fundamental courses according to me? I've color-coded these. Okay, according to you, which do you think are the most fundamental courses? Yeah.
The data structures.
Data structures, right? Anybody else, any other course? Programming language? And by programming language, I don't really mean the programming language course necessarily, but also any course that teaches you Java, 401 thing, also a programming language course. But data structures is important. And if we are talking about data structures, we are talking of using certain abstractions and building certain abstractions. So data structures is about abstractions and also about algorithms. Okay, so I think you picked the right course that way. That when we say data structures, it is both abstractions, whether it's a stack, queue, or even a good old array. Okay, and we're talking of sorting and other search algorithms, right? So it's got to be the fundamental, and that is and abstractions is what you learn in programming languages also. And the difference between compilers and programming languages is you learn abstractions in both, but in compilers you learn how they implement it also. Okay, so we need to know algorithms, we need to know abstractions, and we would ideally, to really know abstractions, we'd like to know how to implement them. So personally, I think everybody should take a compilers course, because the only way to understand a programming language is to understand how it's implemented. So here I am, I learned my first programming language was Fortran. I was an engineer. And yet I dare to go and teach about Java as if I'm an expert. And I can't keep up with all the documentation. But the reason why I feel comfortable is because I've implemented compilers. I know how things are implemented, so I have a good sense of how people might design things. So that is my conceptual base. And given that and given constraints, I can sort of reason out what Java would do rather than have to look it up and Google it. Okay, so implementation is maybe a second level thing. You need to know how to use an abstraction. You need to know how arrays and loops work. Ideally, you should also know how they are implemented inside the compiler. And certainly algorithms. Okay, so my color coding is that I'm surprised. This was supposed to be the same color as this. Okay, so I should go and correct that. But this was the most fundamental. And these are also fundamental. Operating systems will tell you how threads work, are implemented, and maybe a programming language will tell you how threads are to be used. Okay? So, what we're going to do in this course is a bunch of layers. Okay? And abstractions like arrays and stacks, that's the abstractions you learn in single computer programs. Now we're going to talk about IPC abstractions. Okay, with all the fun stuff, blocking, non-blocking, byte transfer, object transfer, even we'll talk of remote method calls. Okay. And then we'll talk about consistency algorithms. Okay, these are algorithms that have to do with making sure that information is consistent and fault tolerant, but not Byzantine faults. Okay. And when you talk about, even in data structures, not only do you learn how to you learn how to implement data structures, you also learn the behavior of data structures. So it's important to analyze these abstractions and algorithms, learn how they work, learn how to analyze them, and learn how to implement them. Okay, so these three aspects will be there in this course applied to distributed computing. Okay? So we'll do design, analysis, and implementation of IPC abstractions, and we look at design, analysis, and implementation of consistency algorithms. Okay, that's a lot to do. Okay, but we're going to not do. We're going, it will be manageable. Okay, and here's a picture of what exactly. So you talked about this distributed file system, right? And most of your programs you will run on your own computer. Okay, that's just because it's quicker. But there will be at least one project where you will take what is called a cyber infrastructure, which is basically a cloud-based infrastructure that allows you to fork processes, create virtual machines, share data, and run things quote unquote in the cloud. Okay, and this is an NSF-supported infrastructure, and I have some collaboration with these guys. The one we're going to use, it's called Atmosphere, and you will use that for one of your projects. So you learn, at least if nothing else, you learn how to use such an infrastructure. Even if you learn nothing else, okay, you learn how to create virtual machines, how to go and run programs on different machines. Okay. Then I talked about I/O, that IPC being basically distributed I/O, and you guys, some of you have studied sockets, but sockets is sort of a slow way of doing computing because there's two blocking. There's degrees of blocking, by the way, and NIO is this total non-blocking form of I/O. NIO means non-blocking I/O. Okay. And it's not an easy thing to master. So your first assignment is going to involve Java NIO. And that's where you'll deal with threads. You'll deal with, if you've just studied the producer-consumer problem in a very abstract way, you'll see the producer-consumer problem again and again and again in your applications. Okay? And so that's something, so that's one there. Now, NIO is byte level transfer. You might want to have object level transfer, and that's what's called a serializer. So converting JSON into bytes is basically doing serialization. Converting your SMTP messages into bytes is serialization, but that is very application-specific serialization. This is application-independent serialization. Okay. This will be an extra credit assignment. So that's important. That there'll be some extra credit and there'll be some regular credit. Now, but you learn what a serializer does even if you don't implement it. Now, to do your own serializer, you need to be able to make it work with. We'll also look at remote method invocation, which is this remote procedure called RPC. And the idea there is that one process will just invoke a method in another process. None of this. You don't have to go and create socket channels. You don't have to deal with non-blocking issues, thread issues. And in Java, do you guys know what the RPC system is called in Java? Anybody know? It's called RMI, remote method invocation. Okay. RMI is built on top of Java serialization. What I've done, but you can't go and just change underneath the serializer for RMI. So what I've done is I built my own RPC system, which I call Gypsy, and it's in Java, and it is customizable. So you basically, and Gypsy's RPC works much like Java's RPC. So you're going to, in that system, you will replace Java serializer with your own serializer, for those of you who do the extra credit assignment. And you will also go and implement your own synchronization of RPC, implement some part of the RPC mechanism, and some part of the message passing blocking semantics. So there are these colored things tell you how this course is like a compiler course, where you're learning how to implement IPC abstractions. Not just using them, but you also learn to implement them. Okay? So there's a compiler aspect to it also. And you'll also learn how to use these abstractions. Then these blue-colored ones are talking about algorithms. So you learn just about asynchronous broadcast, which is saying, hey, I'm just sending the information, hope everything's fine. Okay? Then we look at another degree of consistency, which is atomic broadcast, making sure that information goes either to everybody or nobody. Okay? And then we're going to talk of two-phase commit, where somebody can veto and say, I really don't want I can't accept this information. So this is Actually, the two-phase commit is more like information going to everybody or nobody. The atomic broadcast just makes sure that the order is the same at every site. Okay? So we want to make sure that there's not only, when you have two processes, we make sure that the messages that are received are in the order in which they were sent. Atomic broadcast makes sure that the group of processes agree on the same order of messages. Okay? And the two-phase commit is the one that goes and says, even though the word atomic is with the other one, that everybody agrees or nobody agrees, and one of them can veto also. And then there's an algorithm called Paxos, which is the algorithm used in AWS and Oracle and other places for consistency in the data centers. It's a non-Byzantine algorithm. It's a complicated algorithm. It's a small algorithm, but it's complicated to understand. We're going to look at that algorithm. We're going to look at that. We're not going to implement that in your course, in your project. You will implement two-phase commit, atomic broadcast, and asynchronous broadcast, but you will understand the properties of Paxos. Okay? And all of this will be done in the context of a simulation. So we're going to take a non-distributed program and make it distributed. And you're going to, you're going to you're going to need to know very little about that non-distributed program because it's layered. It was part of a 401 project. So it was done modularly enough that you just need to get certain events and send them across. But it will be, that particular project I'll just talk about soon, will let you visualize inconsistencies very easily. And you'll be able to demo them and show them, create inconsistencies when you're using an inconsistent abstraction and then show how those consistencies can go away with a better abstraction. Okay? So that's kind of an idea that we're going to learn how to use certain abstractions, learn how RPC works, learn also how some aspects of RPC are implemented. We're going to implement three simplistic algorithms, relatively simple algorithms for consistency, and learn the semantics of a more complicated algorithm. The implementation I'll give to you. Okay? So the main point is that we are balancing out algorithm systems together, and in algorithms you're learning both properties of algorithms, like Paxos, and also how to implement certain algorithms, like two-phase commit and atomic broadcast. In abstractions, you're going to learn how to use serializer, okay, communicate objects, and if you do the extracurricular assignment, also how to implement a serializer. Okay, so there's some choice there, but that's sort of the scope, that all these things will be tied together by a common project. Okay, so if you think programming is fun, then this will be indeed a fun course. And if you want to learn more about systems, you'll certainly learn a lot about systems. Okay, questions? Yeah.
Is there a reason for the different colorization, like two different blues and two different oranges?
Yeah. So you're not going to implement Java NIO. You're going to learn how to use Java NIO. Okay. You're not going to implement cyber infrastructure. You know how to use it. There is some gypsy IPC part that you will just use, and these three parts come by default. There are default implementations of them, and you will replace them, and that you will implement. Paxos is light colored, which means you just learn how it works. Okay, and the other ones you learn how they work and you implement. That's a darker. Okay. So this was the picture we pretty much ended at. It tells you what you'll be doing in your in this course. So what I've done is I've color coded systems-like things in pinkish, reddish color, and algorithmic things in bluish colors. So the stack that you see has these bluish colored things and these pinkish, reddish things. So that's the systems and algorithms. And the light red or pinkish stuff is stuff that you will get to use, but not get to implement. And the darker ones are parts that you will get to implement. Okay? So you'll implement the custom serializer, and you also get to know what a serializer looks like. But you won't implement Java NIO, you'll just get to learn how to use Java NIO. Okay? You'll implement atomic broadcast in two-phase commit, but you'll use Paxos and not implement it. Okay? So what you have to do is not only, so what you're learning in this course is, how are these abstractions designed, or how these algorithms designed, analysis of them, and possibly implementation. Okay, so the implementation only is done for the darker colored ones. Okay. So any questions on this part? Okay, this is review. We did it last time. So if you're going to do analysis, you might think of doing proofs, or you might think of writing documents. But the way we will do analysis is through videos. Okay. So what you'll do is you'll take running. In all of these cases, you'll have implementations. Okay. And rather than going and creating paper timing diagrams saying if we did this, this is what happened, you'll just use the debugger with breakpoints and demonstrate what happens, or you will run performance experiments and say, look, this is the data I got. Okay, so you'll actually provide a narrative where you're saying, okay, this is how, by the way, I designed what I implemented. This is the design that I used, and this is sort of the traces logs from it. And typically the analysis involves either performance or inconsistencies and consistencies. That look, in these conditions, with this algorithm, I got an inconsistency, and with this algorithm, I did not get this inconsistency. Okay, and we'll be evaluating your videos. Okay, so I'm just showing you here one example of a student who was doing this. I would really like you guys to have audio there. But this student was using captions. So because he was using captions, I could actually show you what he was saying. If it was audio, I'd have to play the video. But that's the basic idea. Okay, and for each assignment, I'll actually tell you what you have to demonstrate. So if you go to assignment 1, you look at the video part and you'll see this is what you have to demonstrate. Okay, does that make sense? Does that sound attractive? Doing a video? No? What's your concern? Sorry?
Let's see how it goes. I don't know yet.
You don't know yet. So, there's many ways to do this. I think this is really good for you. Okay. Have you guys ever done demos in classes? So demos means that I have to be there, and we have to find a time, and if it breaks, no, sorry, when it breaks. So, but you guys have many paths in front of you. You might go to industry, you might even go to grad school. But if you are practical, you'll be building systems. And, you can go and build the system and build beautiful software. And, if you've done 401 with me, you know how much I appreciate good software. But ultimately, you'll have to explain what you're doing, okay? And what I found is that, as engineers, we tend to be nerds and tend to be more introvertish, and we believe in doing rather than talking about things. That's what the liberal arts people do. But talking is important. And that is when you really realize what you did. So you will realize that if you go to conferences, you have to go and demonstrate software. If you go to industry, you have to demonstrate to your bosses, you have to demonstrate to customers. I've spent time at Microsoft, and there's a tech fest where people go and, explain things to other people. And when I was there, Bill Gates was still there. And when Bill Gates would come by, they'd all start shivering, are we going to be able to explain things to him properly? So this is a very low stress thing where you're just doing it on your own. And the nice thing is, tomorrow you're going and you want to show off what you did. You've got a video to show, to point people and say, this is what I did. Okay. So for me, watching a video obviously means time, and each student creates pretty much the same video, so it's not the most exciting thing you would think. But I really enjoy that because I just see students who were quiet in class, weren't talking, just flower in the video. Okay, so I want to know how it goes. But I think almost every student who's gone through this has really appreciated that. It's work. You have to make that into a 5-minute or 7-minute video, so you'll have to really do some video editing too. But it'll be, you'll really show off what you did, and I think you'll like it. Okay, questions? So anyway, I'll put these slides on, like I said, in YouTube and on my webpage, and you can see the kind of things that goes on in the video. And in addition to that, so here's sort of the video explaining how the performance went. Okay, so look, this algorithm took this much time, this algorithm took that much time. And typically what you'll find is that the algorithms providing stronger consistency guarantees will take longer time, and the ones that provide fewer ones are more efficient. Okay, so that's the kind of thing you want to see also, and so that's the difference between this course and a course that Jim Anderson is teaching to grad students, where you tend to do more proofs. Okay, in both cases we're doing formal things that you're actually implementing. So there's actually a formal piece of code or formal description explaining what you did, but in one case it's sort of both more paper based. Okay. So, getting distributed programs correct is not easy. It's not that hard either. I don't want to scare you guys off. Okay, grading them is going to be even more interesting with all the timing issues that can arise. So I've been working quite hard on getting a grader working for this also. For those of you who've done 401 with me, I've got a grader for that, and that creates its own problems. And we did this last semester. Last time I taught it, we started grading, creating a grader for it. And this winter vacation, I also created part of the grader that you can run on your computer. Okay, so you'll be able to run the grader to see how far you've got. These are JUnit tests using a framework that I've written, which is more flexible than JUnit, which is sort of a layer above JUnit. Let's put it this way. Okay, so the how to get the tests. Those tests still have to be debugged completely. So in fact. So there's two reasons. So you guys like the idea of having local checks that you can run on your computer? So what's good about that? Feedback, right?
Yeah, you know if you got it right.
You done, and so it's you get to know how much you've done, and when people see all greens, they're just so happy. It's a great feeling of accomplishment. More important, mostly you'll get it right. Okay. So what's good from my point of view is that you will debug the tests also. So when you see something is not green, most probably the checks are making some assumptions that shouldn't be made. Okay, look, so how hard do you think is conceptually writing a grading program for writing a grading program in general, regardless whether it's 401, 533, just writing a grading program? How hard is it, do you think? Sorry, which?
It's pretty hard because there's no real consistency with how one person will write versus another.
Okay, so if there's creativity and multiple solutions possible, then that's an issue. Assuming that there's no creativity, there's an exact solution expected. Yeah.
Why not that hard? Just because you have to provide a certain amount of inputs and then you expect a certain amount of outputs.
So just look at the input-output mapping. But does the program typically take only one sequence of input, or does it support more than one sequence of input? So, how many of you have done what used to be called 181, the automata theory Turing machine course? Ever heard of the halting problem? What is the halting problem?
Do you know if the loop is infinite or if it's ever going to stop?
So you can't even tell if the program is going to stop. So so you don't know how many inputs there are. You can't just take one input. You have to sort of, and even if you take one input, you don't know whether it's just, taking a long time, and you can assume there's a timeout. But in general, when there are loops, you can't analyze the program. So you just make assumptions, okay? And these assumptions may or may not be right. And your code can have bugs. Any code can have bugs, right? So just be aware of that. So if it looks right to you, and the grader says no, most probably the grader, that's when you tell me, okay? And we'll either take the test out or we'll change the test, okay? But still, it will be useful, I think, okay? I've done it for assignment 1, and I hope to be ahead of you and do that for assignment 2 too soon. But for now, assignment 1 should be. Assignment 1 is all we need right now because assignment 2 hasn't even been given. Okay. So debug your programs and evaluate your progress. That's good. And debug our tests. Both things will happen. Okay. So is that sufficient for evaluating work? Not quite, because we want the videos too. So I had the slides reversed. So both things have to be done. And the analysis part is what goes in videos. Okay. And here's how we'll have a grade assigned. So midterm and final are 25% each. Okay. We'll have quizzes. Okay, and they're 10%. Okay. Assignment correctness judged by the grader is 25%, and video is 15%. Okay. I think that's a fair allocation, and you'll mostly be getting full points on the assignments. Okay, that will happen. The quizzes are going to be open book. I really would like, and that's happened in previous classes I've taught, for you guys to be talking to each other, and so that's the point, that a lot of interaction will happen in class, and some people talk, some people. When I've taught 401. Few students talk, and a lot of them don't talk because the quizzes are kind of more direct, from the material. These will require more thought, so do pay attention. And they're 10%, so it's not as if it's a lot of credit. But I'll talk about why quizzes are important. I'll talk more about why quizzes are important a little later. Okay, so that's the regular credit. Lots of extra credit. Okay, the total amount of extra credit is more than I think the final exam. So what I've always dangled as a carrot is that you do all this extra credit and you don't have to do the final, and students love that. Though I believe that exams, if you don't prepare for exams, you really haven't learned anything. A lot of you are here because you love systems, love to implement, but you can just implement in industry when you go out to work or anywhere. So if you can't abstract out what you learned, then it's only so useful. Okay, it's still useful, but it's only so useful. So I like exams, but you'll have these quizzes. So we will abstract out what you learned. So for some subjects, you won't have a final exam also, in addition, and that's okay for me. And like I said, I really believe in assignments. So if you guys get more enthusiastic about the extra assignments, I'm happy. And you'll see that you can do both. Okay, so if you have the time, and it's mostly time because there'll be a lot of help, you will get an A. Okay, the question is whether you'll have the time or not. Okay, and again, if you're careful with your time, you allocate it properly, you talk to people, talk to me, it can be pretty efficient too. It's not that you write a lot of code. Okay, it'll be complex code, but it won't be a lot. Okay, so if you've noticed, I have gone and given you both I have released 2 quizzes. One quiz I'm saying is part of the regular credit, and one is extra credit. Okay, so you do that, you get points on top, and I put the extra credit quiz date a little late so that you don't feel pressure on it but it'll be good if you do both quizzes at the same time, if you have the time, if you have enough time in the beginning, because they're very related to each other. Okay. So there is this civilization assignment that will be part of the extra credit, and there'll be an extra credit Paxos assignment too. So there'll be 2 assignments that will be extra credit. The other 2 extra credits have to do with class participation. Okay. So I talked about why videos are important. Why is now a lot of faculty members like class participation. I think that's kind of a given. But let's try to figure out from first principles, why is class participation so good? I mean, if you do the assignments, do the exams, who cares whether there's class participation or not? Yeah.
Well, it shows your engagement in class.
Shows your engagement in class, right? Yeah.
You get feedback on what the general students aren't understanding.
I get feedback. Yeah. Yeah. Anything else? Yeah.
Most of the time, someone else probably has the same question as you, but just isn't asking it.
Right. So that's the thing. I always tell people, there's no such thing as a stupid question. If you asked a question, there's at least 10 other people who had the same question but didn't dare to ask the question. Okay. But this class, yeah. Okay. So that's it. Other things. I said videos are important because it increases your verbal skills. Class participation, especially in a small class like this, where it's non-threatening. Even if you're a shy kind of person, you can sort of probably grow out of it. So there's 2 kinds of class participation that we have. One is, so asking questions is less demonstrative of your capabilities than answering questions. Okay? So every time somebody answers a question, to me, that's like answering an exam question. And I would like to give credit for that. Okay? Also following along what's going on in class. Okay? So you will see that I have all this material recorded. So there's no real incentive to take any notes. Okay? And I do want to encourage people who want to just think and not take notes. Okay? But sometimes, even if all the material is on the web, it's good to write it down, because that means it went in, sunk in a little bit, and then came out in your own words. Okay? Now you may not like it. Okay? It may just stop the flow. You know, when we're having a conversation, you don't start taking notes. So you may or may not like that. But I used to have extra class participation credit only for answering questions. And then I found few students would just give in all the questions and answers. And they found it worthwhile to do so. So I said, okay, if you want to do that, 5% you get for just transcribing the questions and answers. Hopefully not just transcribing, but writing them down. And then 5% you get for your answers. Okay? So that's an incentive to pay attention and to really be in class. I mean, I'm not going to force attendance in this class. And if I force attendance and you just sat there and thought about things that are irrelevant to the course, that doesn't serve any purpose. So this makes sure that you have logical attendance, not just physical attendance also. Okay? So this is extra credit. If you don't like it, don't do it. You want to spend more time doing the assignments and doing the quizzes, you're welcome. But this is yet another avenue for you to do this. And in 401 I did this, and there was just one group of students who did this, and they got their 5-10%, and other students spent all their time on extra credits. Yeah.
Does this include Piazza? Because I know some classes that use Piazza for participation.
Yeah, so I'm talking of in-class stuff. Okay? I'll have a fudge factor where I sort of take other things into account, but I have so much extra credit that I don't expect to use fudge factor. Yeah. So students often come to me and said, we missed this quiz, we missed this thing, this happened. Can we do anything? We've got so much to do. Okay? Now don't ask me for anything more. Right? So left to me, I would love it if you all got A's, and that kind of happens in 533. Those who complete things do get one way or the other. So, but this is yet another way to get. And you will put this diary in Piazza. If you look at my syllabus handout, it tells you exactly what to do. Do this. So this means that every time from now onwards, whenever you answer a question, make sure that you go and take it down. Okay, if you want points for that. I will probably remember that, but that's not enough. I do want to give you credit for actually taking the pain of doing so. Yeah.
Wait, so if we answer a question, we have to write it down and post it on the answer later?
In a private diary or public diary. If you want to make it public, that's fine too. Yeah. Just go look at the syllabus handout. I've got details on that, examples of that. So I understand that's going to break the flow. Okay, but this is an option, and the thing is, what I've noticed is that somebody answers a question, and then next day I ask the same question, a different thing that requires that question answer is related to that, and they don't remember their own answer. And I say, but you said this last time. So I would like things to sink in a little bit. So that's the goal. Okay. Question? Yeah.
But only count the question if the answer is right.
No, whatever your answer was. There's no real right answer to many questions. So I want to encourage class participation. So I do want to, in the diary of all questions and answers, if there was a question and there were 5 answers, just put the answer that was deemed to be the most correct. But your question and answers, go ahead and write down there. Okay, so, and we'll just be going and looking at the number of answers. We're not going to look at the quality as long as they're relevant. Okay. So many ways to succeed. Okay, that's very important. And as I said, the extra credit is greater than the final exam. So that's a good carrot to do these things. Okay. So why class participation diaries? Instructor needs feedback. Learn to speak in public. Okay, that's very important. If you attend any talks, you would see very few people ask questions or answer questions. And ultimately, the way you'll stand out, whether it's in academics or industry, is by being a squeaky wheel a little bit. By being bold and saying things. Okay, So like I said, as engineers, we are more doers and we say just judge our work, but you've got to sort of show off also a little bit. Okay, and this is like, again, if you do PhDs here, or if you do any kind of research course, often there are oral exams. Okay, so getting practice with answering questions here really prepare you a little better for oral exams. Okay? And we just see certain cultures do so badly at oral exam and certain don't, and certain kinds of students. So this would be good. So I said logical was the physical attendance, and recruiters typically often ask me questions about when I write reference letters. What about the oral skills, the written skills? And I say, I don't know. I mean, yeah, they answered the exam questions well, but I don't know the oral exam questions well. So this will give me a basis at least for saying, they participated in class. And there was an NSF survey I just filled which said, what are you trying to do to improve verbal skills? So that really meant that one should do something. Okay? And again, there are trade-offs in it, life and everything. So if you really don't want to do this, this extra credit. Okay, so I talked about what this course is going to be and how I had to go from first principles to figure out what this course should be, which means that there was no textbook that had the answers. Okay, so what kind of resources do you have? So I taught this systemy, this kind of approach where the systems and algorithms combined together with implementations at a graduate level for 2 semesters. And there were many undergrads who took this course, and they did just fine. So that made me bold enough to try it for undergrad. And I've had 2 experiences there. You're always learning. So I expect to learn even more this semester. So this is not in a vacuum. I've got some experience. It means I've got some material also. And a lot of faculty members will post their PDFs of slides, and that will be available to you. But the PDFs are not going to be very useful. You notice that I'm saying a lot, which is not in the slide. Okay, I don't like to create very texty slides. Okay, that just puts people to sleep anyway. So you need to know what I was saying about the slides too, right? And you will have the PowerPoints of the slides. And why are they useful? If you notice here, there's this recording. So those of you who've done 401 with me know that Microsoft has this ability to Microsoft PowerPoint has this ability to record you when you're presenting. And I've been trying to get all my fellow faculty members to use it, but I can't get them to do so. Okay, but those of you who've done 401 with me have seen that this can be useful. So you can actually, what happens then is that when you do a slideshow with recorded PDF PowerPoint, you just put your hands in your pocket and it just goes at the speed at which it was recorded with the narration and the animations. Okay. So that's going to be available to you. But the trouble is that sometimes you want to just look at one particular slide and look at the audio for that. And what you can do is escape out of the presentation mode and just go and click on this particular thing, and it'll just provide you the recording of that particular slide. Okay, that you can fast forward. And so if you think you know what the text means for most of the slides and just a few slides you need to know what the audio was, you can just go. But you can't do 2x or 4. So I also created YouTube videos out of these, and now you've got the full YouTube capability to watch them as you feel like. Okay. So now these are not videos that I've recorded in a studio with beautiful sound and a short amount of very crisp sentences. This is what the live lecture I gave. Okay, this is a live lecture. Most probably my voice was recorded properly, but any questions that were asked probably was not so. So you'll have to live with that part. Okay, and while somebody's answering a question, please think about how you would answer. So these slides are not just dumping out information. These are all question-answer based. So I'm asking a question, students answering. Then I go and summarize the answer. So that's when you get to know what they really said. And while they are answering, think about it yourself, and that's the best. That's a good way to learn. Okay. So so that's sort of. I'm just giving you the caveats. Okay. Plus, there are some written documents. Ideally, the written documents are the most effective way of learning. Well, some people like the audio. but written documents are quick to read, and they are not complete. But much of the material has written documents. And also, one student, as I was walking in, said, I looked at your assignment, it's really long. It is, right? But I'm explaining a lot of things. I'm telling you how to run the local checks, telling you how. But one of the reasons why it's so long is because I'm telling you how to do it. And I'm, in fact, abstracting out all the material that you have to look at in YouTube videos and other material that is necessary for the assignment, so that maybe you don't even have to look at that material or remember that material too much. You've got the relevant part right there. Okay, so the assignment description itself is another resource. Okay, where I'm telling you what, if you look at this, has anybody seen that part where I'm explaining at the end, how to do it? The relevant material. Just have a look at that. I mentioned that there. So that's also a way to get information. Okay, questions so far? Okay, now there's many ways. There's multiple modes of information retrieval, and there's videos, there's written documents, there's something in the assignment. So what exactly do you need to know? Because there's not one source. So this is where the quizzes become important. Okay, the quizzes capture what you have to know. Okay, so if you know what the answer to the quiz is and why the answer is what it is, you know the material. That's what I'll test you in exams, and no more than that. Plus the assignments. So you need to know enough to do the assignments, and you need to know enough to answer the quizzes. Okay, so you can work from that point of view. You can look at the quiz and say, okay, what do I need to know? Let me find out, let me find out the answer from the PDF. Oh, I couldn't find the answer from the PDF. Let me go to the video instead, or let me go to the written document. So that's why quizzes are really important. Okay. So not all questions can be answered based on posted material. Some require you to make some inferences, and that's why. So you might have to Google. Okay, and this is all open book. You might have to think and say what makes logical sense based on what I know, and talk to others. Okay. Now, given that there are all these resources, the question is, what do we do in class? And what I'm plotting here is the value of a live lecture without existing resources and with existing resources. So if I did not have anything on the web, a lecture would be very, very important. Right? Otherwise, you get no information. If I've got the information on the web, a lecture would still be useful. I'm just not going to have zero value, but it won't be as useful because you do have information from the material. So can we go and make better use of class than just give live lectures? Okay. And what we'll do is, and it's kind of worked, in my opinion, well in my other classes, that you look at the background material, you'll try to answer the quizzes, and after you answer the quizzes, I'll first kind of give you a motivation on why that next section is important. Okay, so that's going to be done live. That then you'll do the quizzes, and I'll be around. I can ask me questions. You'll ask each other questions. You talk to each other. Then you submit your quizzes, and then we'll discuss it and do a post-mortem of the quizzes, and discuss the quizzes, and so that will be the live interaction. Okay, so the classroom will be used for conversations among yourselves. Okay, and the conversations do not have to be restricted to quizzes. They can also involve your assignments. Okay, and also doing the post-mortem of the quizzes. So the quizzes are going to be multiple choice because Sakai, I want them to be graded easily by Sakai. So they won't tell me why you chose answer C. Okay, was it just because that's typically the right answer, or because you really knew what was going on? So in those discussions, we'll discuss why C is the right answer. Okay, and that's where you'll get to show off and say, okay, I believe this is why it's the right answer, and that's when you write it down in your Piazza post, whether it's correct or not. So that will be the mode of operation. And there'll be some material that I might present fresh, like I was thinking of blockchain. That a lot of guys mentioned blockchain. So that would be something we can talk about. Okay, and so some new material, but mostly we'll do this. Okay, and one advantage here is do quiz collaboratively. or use class time for other 533 based. So what will be ideal is that if you look at the material and type the quiz on your own before coming to class, and then thrash out the correct answer in class, that will be the ideal thing. I know that requires discipline, but people who've learned the most from this kind of course have done that. And please don't commit to the answers before you discuss. Okay, now I don't have negative points, but there are some questions in Sakai that have got multiple answers, and Sakai does not give me an option to remove multiple negative points from those kind of questions. I either have an option saying all or none, or right minus wrong. Okay, that means if there were 4 correct answers and 4 things that had to be ticked and 3 things that didn't have to be ticked, and you got some right and some wrong, they won't just give you points for the things that you got right, because then you can just check everything. They'll give you points for what you got right minus what you got wrong. So be careful with those questions. Okay, and again, it's only 10%, and you have a lot of other ways to get points, but let's not just give away points. Okay, and in this class we've got 2 prerequisites, and some have done one, some have done the other, and some are actually doing it as a co-rec right now with special permission. So by having this mode of operation, it levels the field. Okay, you go and look at the material on your own. Now you know as much as anybody else does who might have looked at the material, learned the material in another class, and then you can answer based on that, having as much knowledge as anybody else qualified to answer that question. Okay. Any concerns? Okay. And if something is really going bad, let me know. So what do you think is harder for me, to just give you live lectures or do this kind of, for me, from my point of view? Or do this kind of mixed mode instruction?
I think the autograder is the hardest thing for you.
The autograder is hard, but what about just this lecture kind of thing? Yeah.
I mean, at least from myself personally, like that takes a lot of time outside of the lecture, where you know this material. If you want to do a live lecture, you could just show up.
It's not quite that. I actually calculated when I was first became a professor. So when I first became a professor, I never taught before in my life, in fact. And I was teaching this book on this teaching operating system where actual code was written in the book, and I'd never seen that OS before, but I took it as a challenge. Nobody after that, I was at Purdue at that time. This was the operating system a guy called Doug Comer had written. And I'm the only one other than Doug Comer to talk about that code. So I would sleep at 3 in the morning and give the class at 8 o'clock in the morning. And I was kind of sick the half of the semester. I was just so stressed out. So that was a lot of work. When you prepare the lecture for the first time, it takes, a 2-hour lecture will take you about 3 days sometimes. Okay. Well, what happens when you've already given the lecture? So I actually created class notes for that stuff. So I just had to go and look at the class notes, right? Or I just knew the stuff. No, firstly, it's not in my cache. And secondly, to me, teaching is acting. You sort of make mistakes, you have pauses, and you have to sort of figure out the whole play and see how you're going to have everybody involved. So it used to take me 3 hours to prepare each lecture, even though I had all the class notes, the material that, from which I taught the previous class. Now when I started recording, it was so cool. At breakfast time, I would go and put on my recording and then figure out what went wrong there and just correct it a little bit and give the lecture. It was just mindless. Okay, it was fun because for you guys, for the students, it was new, but for me, it was old. But if you teach it once a year, of course, it's not too old. So that's easy. It's a straight path. This is kind of complicated. We are trying to do many things. Give a live lecture also, have quizzes. So it's a lot of stuff going on. It's like a distributed system, right? There are multiple things going on. It's not a linear kind of progress. So from my point of view, if things are really going bad, let me know. I'll just start lecturing. It'll be easy. I'll go to sleep for the rest of the semester. It'll be easy. So I'm trying to do something harder just because I think this is important. That's why I've done all this work for this course. And I wanted to sink in. Okay? And it's important from a practical point of view that your future can get influenced by how much you know in any course, but in this course particularly. A lot of students have got jobs, based on what they learned in this course, because distributed systems is something people don't understand that well, and this is really relevant. Okay, so if things aren't going well, let me know. Okay, and we can go to another mode. But and especially that will happen if you guys don't talk to each other. So I really would like you guys to sit together in groups. One group can be sort of facing this way. So this kind of desk will allow that to happen. That you guys can be facing each other and Okay. So Piazza for announcements, and there's a course page. And collaboration. I want you guys to collaborate as much as you want to, as long as you don't copy code. Okay. And so typically my assignments are pretty much telling you how to do things, but in English, and you'll translate that into code. And when I was a grad student, my favorite course was compilers. And in compilers, that's what happened. They would tell you the algorithms and in the book, and you just had to translate that into code, which was not a trivial task. But you kind of knew where you were going. You felt good about where you were going. You knew that was sort of there was a good structure. And so that's the principle here, that, there's not too much thinking and, algorithms. I'm not judging you on your thinking necessarily, but more on your implementation. There are some thinking aspects. That's where you can talk to each other and talk to me. So I'm not just giving them away, but I think just translating these concepts to code, there's a lot of learning. Okay. Again, you can talk about what questions I asked in class. Probably you won't, because that's such a low fraction of your grade. So just don't share text of question answers also, okay, in the diary. And you can look at each other's code and help each other debug, but that's not going to make you subconsciously go and reproduce that code. Okay? Though I have seen in pop music, people argue that, I just subconsciously plagiarized that song. Okay? So, and like I said, assignments may contain solutions in English, and I would encourage you guys to first try to think of the solution on your own, and then go to the solution that I've given in assignments only as a second resort. So think on your own. But okay. So that is